we'll probably have the last discussion on vibration and vibration rotation spectroscopy today, and then we will move on to Raman for 2 days, and then electronic spectroscopy following that. But then, since we already have learned how the rotation works, how the vibration works, from now on it will be much faster for us to take on what's happening in electronic spectroscopy. We probably will use the same concepts, but we will just see how it's applied to transitions between fluids and electronic levels. You will still see vibration transitions, you will still see rotational transitions, you will see OPNR branches, and more importantly, you will see the formation of band heads, which we spoke about. But very rarely you are going to be seeing a band head in an infrared spectrum. You only get a hint of band head formation, meaning you will see the lines getting closer in one branch and opening up in the other branch. But you very rarely will see a turnaround in an infrared spectrum. The reason why that happens is simply because the B1 and the B0 are close, and it's going to take a big J to really make the transition. If B1 minus B0 is small, you need a large J plus 1 whole square to make that really work. And therefore you will find the bandwidth actually turns around at extremely large J. But in electronic spectroscopy, you will see that it's very common, and you will see why that will happen in that situation. So what we will do is we will simply take what we have learned and start applying it to all these situations that we will come across. Before that, Ajit Kumar. Okay. Tomorrow is your birthday, right? Yes. What are you interested in? Math, physics, chemistry, biology. Physics. Okay, good. Because you have somebody to live up to, Raman. Okay, mathematics. So you have your he excelled in number theory, he excelled in analysis, he excelled in geometry. The Riemannian geometry as opposed to Euclidean geometry was supposed to have laid the foundation for theory of relativity. So you see that Raman also has his birthday tomorrow. Of course, I don't think they have celebrated, but that's his birthday, and you have somebody big to live up to. So wish you all the best. I have a very strong request to make of you. This is not an 8 o'clock in the morning class, it's a 5 o'clock in the evening class. Therefore, I would like you to be on time. At least 8 o'clock, students have been telling me that breakfast is not on time and so on and so forth. But I don't think you have any excuse unless you can make up a real good one for me as to why you can be late for a 5 o'clock class. Very few things in this world that make me angry, but one is when you come late without reason. Like we have some people in train. So please ensure you're on class at 5 o'clock. I'm here much before that. Be here at 5 and let's start the class on time. Okay, so what we will do now is to look at vibrations and look at the applications, some of which you have already done in the lab. So we will see how we can visualize what you have seen there. So far what we have done is we have looked at rotations, accompanying vibrations. We started off by saying that the B0 and B1, which is the rotation constant in both the lower and upper states, are the same. We came up with a very simple equation. But then we said, well, that's not really true because the average value of R does change in the two states, and therefore one should really be talking about B1 and B0 as being two different numbers when it comes to defining the rotational constant for the lower and the upper state. So if you take these two as different and we rewrote the equation and we derive the frequencies for the R and the B branches, we came up with something interesting, and that is mainly the bandwidth formation and so on. So we have done all of that, and all this applies to diatomic molecules. We also said that the only bands that you will ever see in vibration spectra are those in which there is a change in dipole moment associated with the vibration. That's the first thing. Point number 2, you must have a resonance between the states concerned and the frequency of light that you are using for the transition. And the third, of course, is the delta V equals plus minus selection rule for the harmonic oscillator. The oscillator is not harmonic, then of course we have extra lines that kick in, which is going to be the delta V equals plus 2, plus 3, and so on, which are actually the overtones, and you will see them. Hot bands are the other things that one can see, which will be the 1 to 2 transition or 2 to 3 transition. While a purely harmonic oscillator, you will never differentiate because the bands are all equally spaced and all of them just keep falling one on top of each other. You will find that in an unharmonic situation, it is slightly different, not very, very slightly. And I showed you the spectrum of HCM, where you had the fundamental, and right beneath it was sitting the hot band. Not exactly overlapping, but enough for you to be able to discern the two. And the reason why you could discern the two was simply because they had slightly different frequencies. 0 to 1 was slightly higher in energy than the 1 to 2. Because they had harmonicity, the lines tend to, the energy levels tend to pack up closer as you go up. So you could see both the hot band as well as the fundamental. Not exactly overlapping, but somewhat overlapping. You can see all these were for the diatomics. And we also said that the condition that there must be this change in dipole moment actually comes simply because if you were to write the dipole moment and expand this dipole moment around R equals R using a Taylor series expansion plus du over dx x plus 1 over 2 factorial goes on. To begin with, don't worry about this. You only worry about this part. Now, you know what the function probability integral is psi prime mu psi double prime dx. Looking at a one-dimensional oscillator, so I just look at x. Psi prime is the vibrational upper level, this is the lower level, and mu is also the dipole moment operator, which is the one that actually is helping the light couple energy into the molecule. So you have this. What are these? These are the wave functions of the oscillator. You know, in a harmonic oscillator situation, they would be the Hermite polynomials, which if you have done that in your 1 or 2, fine. If you have not done that, don't worry at all. They are just the wave functions for the V equals 1 level to V equals 0 level. Just like you have wave functions for the N equals 1 level and N equals 2 level for your party in the box situation. We are not really going to be worried about these nature of the wave functions because we don't have to. We can still make the conclusions that we are setting out to without knowing what really psi prime and psi double prime actually are. So when I do this, what happens? I'm going to take mu and take the first two terms and put that out here, and that's going to be equal to mu e plus d mu over dx into x. Get this out, and you will find that's going to be mu e psi prime psi double prime to dx, that is this, and this. But mu is a constant, I pull it out, and it stays out, and I have psi prime psi double prime dx. What's the next term going to be? The next term is going to be du over dx, and it's going to be psi prime x into psi double prime. This is basically what that equation or that integral turns out to be when I expand the dipole moment around mu equals mu at R, mu at R. What can you tell me about the wave functions for the n equals 1 level and n equals 2 level in the particle in the box? Psi for n equals 1 and psi for n equals 2 are cognitive. And I don't know whether you were taught that if the matrix, if the operator is Hermitian and in the two levels, let's say the operator is Hermitian and you have two levels, like the particle in the box, n level 1 and level 2, n equals 1 and n equals 2. This is the wave function for n equals 2 level, 1 level. This is the wave function for n equals 2 level. And these two levels have different energies. They are not degenerate functions, they are two non-degenerate functions. So if I have a Hermitian operator with the Hamiltonian is, and the levels are non-degenerate, then the two functions turn out to be orthogonal. And actually you can want to prove it. So if these two are non-degenerate levels, then these two functions which correspond to those levels must be orthogonal. A condition. What happens when the two levels are degenerate? Do they have to be orthogonal, or do they have not to be orthogonal, or what is it? If you had told me I don't know, that would have been the perfect answer to that question. When the two levels are orthogonal, and the two functions you come up with, we don't know, they need not be orthogonal, they may be, they need not be. But if they are not orthogonal, you can always reconstruct two functions from them, linear combinations that turn out to be orthogonal. So for degenerate levels, you are not assured of orthogonality. That's why I think you said I don't know. That's right. But you don't know at that point in time. You check for orthogonality. If they are not orthogonal, then you can actually take those two functions and construct two linear combinations from them in such a way that the two functions you now have constructed turn out to be orthogonal. Keep that aside. Non-degenerate levels, they have to be orthogonal. You know that. So in this case, what happens? This is for b equals 1 and this is for b equals 0. Are they degenerate or non-degenerate levels? They are not degenerate levels. And therefore, what can you tell me about their orthogonality? They have to be orthogonal. If they are orthogonal, what happens to this guy? At 50 goes to 0. So the intensity, the transition probability integral now simply depends on this. If d mu over dx is 0, what happens? The whole thing goes to 0. And you don't have an intensity for the transition. But what do you mean by saying d mu over dx is 0? It's simply saying that there is no change in dipole moment during the vibration. This is what I said a little while, few classes ago in English. I just said that the vibration occurs and there is no change in dipole moment during the vibration is not active, infrared active. Vibration is active, vibration will still happen. It just won't absorb light and therefore you will not be able to see it in an experiment that you are conducting. It doesn't mean the molecules are not vibrating, they are still doing that. If you take the carbon dioxide molecule, it's doing this. But while it is doing this, is there a change in dipole moment? No. Therefore, it does not absorb light, and therefore you don't see it in an experiment. But the molecule continues to do this. It's just that you don't even recognize that the molecule is doing that. Why? Because for this vibration, there is no change in dipole moment during vibration. Therefore, d mu over dx is 0. Therefore, this term kills it. What about this term? Well, you can go back and evaluate that. And if you evaluate that term, of course, for that, you will need to know what psi prime and psi double prime look like. But if you did that, if you throw in the Hermite polynomials and did the evaluation, then you will find that this term will not go to 0, provided delta V equals plus minus 1. So all the selection rules, all the conditions that you require for the transitions to be observed are hiding in that integral. The d mu over dx term tells me that the vibration must be such that there is a change in dipole moment during the vibration. The one inside the integral tells me, which is psi prime, psi double prime with an x sandwich, tells me that that integral will not go to 0 provided the two quantum numbers referred to by psi prime and psi double prime change by 1 unit. Delta V equals 1, plus minus 1. So if this is the V equals 1 level, this is V equal to 0 level, this will not necessarily go to 0. If this is 2 and this is 0, it will go to 0. There are many ways of showing that. One way is, of course, using group theory, which you have done to some extent in the last semester. You can use that and be able to do this. But in general, you can actually work this out as a very generalized equation and show that this integral will be non-zero, provided the two wave functions are referring to two levels which differ by one quantum. As long as they differ by one quantum, that integral will be non-zero. So 0 to 2, no way you have a transition. 0 to 3, out. But 1 to 2, yes. 3 to 4, yes. As long as the change in quantum number is plus minus 1, this integral will survive. But this, of course, is the one that determines whether the intensity is going to be great or small, or whether it's going to be zero, because that tells me something about the nature of the vibration. Carbon dioxide, symmetric stretch, no transition, but an anti-symmetric stretch. You will see, because it will change in dipole moment. And the magnitude of this also tells me something about the intensity of the transition. This d mu or dx is large, and actually tells me that this transition can be quite intense. I also showed you what the dipole moment should look like, the plot should look like as a function of x. And what was that? If I take the two species and just coalesce them, x goes to 0. The x actually in this case is the difference or the distance between these two. If that goes to 0, what's the dipole moment? 0. The two species are sitting at infinity and not even looking at each other and don't even know the other one exists. What's the dipole moment? Again has to be 0. Which therefore means that somewhere in between I must have a maximum. Now the question is, where is the maximum? And mind you, this integral has all been evaluated at r equals r because I have expanded the dipole moment around r equals r. Now if my r is here, if my equilibrium internuclear distance is somewhere over here, then what is d mu over dx at r equals r going to be? It's going to be this slope. If my r was here, what is my d mu over dx going to be? It's going to be this value. Both these are non-zero slopes. Therefore, d mu over dx will contribute to that integral actually living. It's not going to crash out. However, if my RE was here, in other words, at the equilibrium internuclear distance is where the dipole moment curve goes through a maximum, what is my slope going to be there? This will is gone. So you can see therefore that this curve actually if you plot for the given system and find out what the slope is going to be at r equals re, it gives you some idea as to what the intensity is going to be. Because d mu over dx actually is scaling that integral and giving you the intensity that you want to see. So in all the calculations where we try to find out what the intensity of the transition is, these are the things we need to do. Find out what the d mu over dx is going to be for the oscillator. A large number, I have a good intensity. Small number, very small intensity. And if it turns out that the maximum occurs at r equals re, then the slope actually goes to 0, and you're not going to see anything in that system, even though the delta V equals plus minus 1 correction rule has been obtained. So you see there are three contributors to the intensity of the transition, or to the existence of the experiment. First is your frequency in resonance. Second, does this vibration have a non-zero slope or change in the dipole moment during the vibration? And third, direction. So till he comes back, let me show you some pictures. what we have done is we've actually calculated the frequencies. I will tell you about normal modes and so on once I get my voice back up in condition. But what I'm going to do now is just to show you what the polyatomic molecule will vibrate like. Again, I'm going to tell you about normal modes and then come to this. But let's see what this is formaldehyde. So you have a carbon, a hydrogen, and an oxygen. And what we have done here is we have calculated the structure using a quantum mechanical procedure, which is embodied in a certain program called Gaussian, which actually was written by Popel in Nobel laureate in theoretical chemistry. And what we essentially are going to be doing is we have calculated the structure, and of course you know what the structure of formaldehyde is going to be. Remember what point group this must belong to? Go back to your symmetry. What point group must this belong to? What does it look like? It looks like water, right? This is just an addendum onto it. So therefore it must be C2V. So it's a C2V structure. And if you have a C2V structure, then let's see whether we can. And for water, what were the vibrational modes we saw? There is three. One was the symmetric stretch, and one was the anti-symmetric, and the third was the bend. And you only had three because the number of atoms is 3 and 3n minus 6 would just be 3. So I will tell you something about normal modes before we come to the pictures. Now that normal surface has been restored. So what we are trying to do is in a diatomic is no big deal. There's only one vibration you can possibly think of, and that's the vibration like this. And however hard you try, there's nothing else the molecule can do. It's just got one vibration mode that you can possibly think of. Water we said has three. And what do we mean by these normal modes? I think I might have told you. This normal mode essentially is simply breaking down of these various pictures that you can think of in your mind to describe what the water molecule will actually be doing. If you had a water molecule hung up in front of you, then you will see that it's going to be doing a very complicated motion. But you're going to be telling yourself that what is really happening is that this complicated motion of water can actually be thought of as a superposition of this plus this plus this. It's like almost like saying, I don't know whether I gave you the example of the pendulum. If you had a pendulum with a string, you pulled it out and left it, it's what it's going to do. In any direction, you keep moving. In other words, whatever vibration it is that you excite is going to be doing that. However, if you had a pendulum with sort of a square bar, a bar with a square cross section, so let's say something like this, assume this to be a square. If it has something like this, and then if I pull the pendulum along one of its sides, and then I left it, this is what it's going to be doing. In other words, I excited this mode, and that mode is what the pendulum is going to be doing. If I excite this mode along this side, then that's what it's going to be doing. But if I excite along a diagonal and left it, it's not going to do this. Actually, it will start doing this, it will go here, it will go there, back, forth, and it will keep doing all this larger motion until finally it will come back and retrace its path. And how quickly it will retrace its path will actually depend on the ratio of these two sides. And if it's an irrational number, then of course it's going to take an infinite number of 10 before it gets back. But the point is, whatever it does, I know I can always express it as some combination of this plus this. In other words, this motion and this motion are the fundamental modes which this system has, and we call that as the normal mode. Likewise, if you take a water molecule and I keep looking at it while it is doing this vibration, it's going to be doing a very complicated motion. But I know all the time that what this water molecule is actually doing is this, and I can, if I add these three, then I'll see the water molecule is doing something this way. But actually what it is doing is a combination of these three, and we say that these are the normal modes. If you provide energy corresponding to one of the normal modes, then out of this complicated motion, that mode alone will get excited. And now the water molecule will do something else. Because I have V equals 1 quanta of this vibration, V equal to 0 of the other two. So in essence, what I'm trying to say is that this complicated vibrational motion which the molecule does can actually be broken down into some very fundamental modes, which we call as a normal. Bigger the molecule, the more modes it has. And that's given by your 3n minus 6 or 3n minus 5